Alright, so we're looking at friction in this video. There's a little couple things to note. Friction always opposes motion. Okay, so here we see that friction always opposes motion, not always the applied force. So something to remember, friction opposes motion. Sometimes, well, let's say usually the applied force is in the direction of motion. So usually you could say friction opposes the applied force, but not always. Sometimes an object is moving one way while you're applying a force in the opposite direction. Maybe you're trying to slow it down and stop it. In that case, the motion is opposite to the applied force. Friction is also opposite to the motion. Okay, so in that case, it'd actually be in the same direction as the applied force. So I'll show you a little example of that when we're in class, and you can ask me about that. There's two main broad categories of friction. The first one is kinetic friction. The second one is static friction. Kinetic friction always opposes an object's motion when that object is sliding across a surface. So as it slides across a surface, kinetic friction is what opposes the motion. Whereas static friction always opposes an object's motion when it's at rest on the surface. So maybe you can picture maybe a table is resting on the floor and you're pushing on the table, but the table's not yet moving. You're not pushing hard enough to move it. In that case, it's static friction that's opposing the motion. It's keeping it at rest on the surface. To carry on with that, there's a special case of static friction called limiting static friction. That static friction is the maximum static friction that the object can resist with just before it starts to move. So again, you're pushing on a table and the table's not moving. You push a little harder, the table's still not moving. You push a little harder, the table's still not moving. You haven't yet overcome this maximum static friction, the limiting static friction. Once you push harder than the limiting static friction, then the table will start to move. Okay, so that's limiting static friction. You can see here, let's just look at this first free body diagram. This is our typical free body diagram, and you'd say, well, normally, normally this force of gravity here is equal to the normal force. That's typically true, at least for grade 11 purposes. Something that we notice, though, is as Fn increases, so as this force here starts to get bigger, then the normal force will also increase. We know that because they're equal. But here's the thing that we notice with friction. As the normal force increases, friction also increases. And we can see that over here with this free body diagram. If I look at this one, Fg has gotten bigger than Fg was over here. Fn has also gotten bigger. I don't know why my subscript here did something weird, but there's Fn. You can forget about that n. This thing has gotten bigger. This thing has gotten bigger as well. So those two always go together. But again, here's what I notice. As Fn gets bigger, this force of friction here has gotten bigger than it was over here. So Fn seems to get bigger, or as Fn gets bigger, Ff also gets bigger. Here's what we see. As Fn gets bigger, Ff gets bigger, and it turns out that they increase proportionally. What that means is if Fn gets 2 times bigger, Ff gets 2 times bigger. If Fn gets 3 times bigger, Ff gets 3 times bigger. If I divide Ff and Fn, I always get a constant. We give that constant a name. The name is actually the coefficient of friction, but the Greek letter we use to represent it, it's right here, we call it mu. Okay, so mu is this funny symbol here. It looks like a U with an extra little tail at the front. That is the coefficient of friction. And just like we talked about a second ago, there's the coefficient of kinetic friction. Well, this is force of kinetic friction. Here's the coefficient of kinetic friction. And over here is the force of static friction. So over here is the coefficient of static friction. So force of static friction, coefficient of static friction. Here's a couple things to note. If you're wondering what mu is, what is this coefficient of static friction or kinetic friction? It's the amount of grippiness between two surfaces. Textbook would probably use a word like traction, but I find most students understand grippiness better. The amount of grip that two surfaces have. So if I wear my good gym shoes on the gym floor, I've got good grip. That means I've got a big mu value. Whereas if I take my gym shoes and I wear them on the ice rink or something, when I'm standing on ice, suddenly I get bad grip. Okay, that means I've lowered the mu value. Low mu value means low grip. I'm going to slide easy. High mu value means good grip or high grip. That means I'm not going to slide easily. The thing to note in that example is if either surface changes, then mu changes. I was still wearing my same shoes, my good gym shoes that are supposed to have good grip, but it depends on what floor I'm standing on. Okay, so if I'm on the good gym floor, I've got a good mu value. If that surface changes and now I'm standing on ice, same shoes, but my mu value has changed because it depends on both surfaces. Lastly, we notice the static coefficient of friction, mu s, is always greater than the coefficient of kinetic friction. So things that are at rest have more grip than things that are already sliding. So we've got a bad student sliding a large 10 kilogram box across the school parking lot. Bad guy. The student pushes the box with a force of 45 newtons. We're told what the coefficient of kinetic friction is and the coefficient of static friction. And originally I'd asked what's the acceleration of the box. We can't actually do that yet. But what I do want to ask is this. What is the net force acting on the box? That's something that we can do. So if I draw, as always, I'm going to start off with a free body diagram. And I want to draw that and I want to find out what forces act on this box. We always know gravity is down. The normal force is going to be straight up, resisting. Let's see if we can make that arrow. There we go. Making it so this thing doesn't fall down any farther. It's just going to stay sitting on the ground. We've got some sort of an applied force pushing to the side. We're not told which side, so let's assume it's this side. And then friction is back this way, just resisting motion. Let's stick some values in here. We know Fg is always mg. We know the mass of this box. We were told it's a 10 kilogram box. Little g, as long as we're on the surface of the Earth, that's 9.8. I always have trouble with these 8s. Let's get rid of that. Make that 9.8. There we go. And we multiply those two numbers. We can say Fg 98 newtons. And as usual, this thing is sitting on level ground, which means Fg is equal to Fn. So Fn also 98 newtons. We're told in the question what the applied force is. That's 45 newtons. So we just need to figure out friction. Friction's the thing we got to find in order so we can add all these forces and find the net force. So I'm going to just come over here and say friction. Just remember, friction is mu times Fn. So the whole reason we had to find Fg was just so that we would know Fn, just so that we can sub it in here and solve for friction. Okay, so friction is mu times that normal force. Normal force 98 newtons. We just got to figure out which mu. Now in this case we're told that the box is sliding. And remember, if something is sliding, we want mu k. So just to be mean, I put mu s in here. We don't want mu s, we only want mu k. Mu k 0.25 times 98. Let's see, if we work that out, that is 24.5 newtons. So there's friction. Remember, friction is not our answer. We want to find the net force. So let's switch this up a little bit, and we're going to say now the sum of forces, all of the unbalanced forces. Remember, Fn and Fg are balanced. I don't need to include those. So just the two unbalanced forces are applied force and force of friction. And we should state our positive direction in here as well. I'm going to say in the direction of applied force, that's going to be my positive direction. Okay, so when I sub these numbers in, applied force, that's equals, applied force is 45 newtons, friction is negative 24.5, and remember, it's negative because our positive direction is to the right. So when I add those two things, let's see, that is 20.5 newtons, and that's in my positive direction to the right. And we should do some good significant digits here. That's about 21, let's say it's about 21 newtons, and that is to the right. And that is our net force. I'll stick a little vector arrow on there just to make sure we know it's a vector. In this question, we've got a book sitting at rest on a tabletop, has a mass of 3 kilograms. Again, we know the coefficient of static friction, coefficient of kinetic friction. Let's find the applied force needed to just start this box moving. As always, let's start off with our free body diagram. And as always, we got a good force of gravity going down here. We're going to have a normal force going up this way. Those two forces are equal. We've also got some sort of an applied force. It doesn't tell us which way this is going, so I'll say applied force is this way. And this thing is not moving, so friction has got to be resisting that. And just remember, if it's not moving, it's got to be static friction. Kinetic friction means one object slides across a surface. Static friction means that the objects are at rest, or it's not sliding. In this case, the book is sitting at rest, so it's there. Applied force, that's what we're looking for. So we're trying to find out, what is this applied force? In order to find out the applied force to make it just start moving, we're going to need to solve for the force of friction. To do that, as is always our pattern, just remember, friction is mu times the normal force. So as is often the case, Fg and Fn cancel. I don't really need to consider them, but unfortunately I need to go through and solve for Fg in order that I can know Fn, in order that I can sub it in to my mu Fn equation. So let's go back here and solve for Fg. The mass of this book is 3 kilograms. G, as always on Earth, 9.8. Fg, 29.4 newtons. And again, if Fg is 29.4, Fn also 29, make that a 29.4 newtons. There we go. Okay, so we do all that, again, just so we can figure out what friction is. Friction is mu times the normal force, and the normal force is 29.4. Seem to have trouble with my 9s here. Mu, we got to figure out again which mu to use. Because the book is sitting at rest, it is not sliding. That means we're going to use static friction. Okay, so this thing now is 0.25 times 29.4. We work that out, let's see, that is 7.35 newtons. That's friction. So now the question is, oh, and I should say this, actually, this is static friction, and because we're using mu times Fn, that's actually going to give us the limiting static friction. Remember we talked about how there's two types of friction, there's kinetic and then there's static. Kinetic is when one object is sliding across a surface, static is when it's at rest, and then we mentioned this limiting static friction. Limiting static friction is the maximum amount of friction that an object that's at rest can resist pushing with. So in this case, if the limiting static friction is 7.35, if I push with 5 newtons, the thing will only resist with 5 and it's not going to move. If I increase my force, my applied force, and make it 6 newtons, static friction will increase to 6 newtons. Again, it's not going to move. I increase to 7 newtons, it increases to 7 newtons. Again, it doesn't move. The maximum it can resist with, though, is 7.35 newtons. So if I want this thing to move, my applied force must exceed the limiting static friction. So FFS lim. My applied force must get bigger than that, so my applied force would be anything greater than 7.35 newtons. What people will usually say then is, you could say 7.36 or 7.350001 or something like that. People will usually just say this. The applied force, it's approximately 7.35 newtons. That doesn't look like a very good 7.35. And then last thing, for significant digits, I suppose we should round this thing and say applied force. It's about 7.4 newtons. Okay, but I'm happy if you say that the applied force is equal to the limiting static friction in order to make it move. In reality, it's got to be just bigger. And that's the applied force needed to start this thing moving.